Okay, people in the line, can you hear me? Thank you. Pardon? Yeah, just chapter 14. Yes, we have some remaining part in chapter 14. Yes, so we have only three remaining class. One is this class, and the next is this Thursday class, and the last class is the next Tuesday class. Then class is just over, and the other remaining one is just exam 4 in December 3rd or 4th. I'm not sure, but yeah, it is about that. Yeah. So that's yours. So thank you. Oh, December 4th. Thank you. Great. Okay, howdy. So I have several announcements today, and the one and big, very important announcement is that please watch the review video. Yeah, as you know from the email, I had a very big mistake on explaining the Hill Huntington method. So I just want to emphasize it again. So what I explained in the last time about Hill Huntington method, what I explained is about this. So when we use the Hill Huntington method, what I was explained in the wrong sense is that we need to round up this Q star, right? But that's not true. That's what I had mistake in the last time. So instead of rounding up this Q star, you can use this criterion that it just compare your Q, original Q with your Q star. And if your Q is greater than or equal to Q star, then round Q up. But if your Q is less than Q star, then round Q down, right? So that's the original Hill Huntington method. And that's why I found that my prescribed answers seems true. But yeah, but in the maybe in the last Thursday I was very busy at the moment, so I just lost in my mind about this method. But that's the original Hill Huntington method. So instead of using this rounding Q star, using the Q that if Q is greater than Q star, then round Q up. But if Q is less than Q star, then round Q down. And all the examples we did with in the last time is also explained in the review video. So please watch it. It doesn't take, in 1 hour, it only takes 20 minutes. So it's very, short, but please watch it and make correct on your examples, right? Again, I'm so sorry about the mistake. Okay, so do you have any question on the last time? Pardon? Yes, everything after the round, everything is same. Yeah, just in the case of rounding, that's the not correct one. Yes. And that's one announcement. And the another announcement is quiz 10 will be in this Thursday, and that's the last quiz we will have in this class. So yeah, it will be on error sign with 2 problems, and so please watch it. And again, this Tuesday is and then this Thursday and next Tuesday are the all classes we will have. And so next Tuesday is the last class. So if you plan to go back to, your country in the Thanksgiving, then please count it on your schedule. And there are 2 more announcements in here I didn't write down. Okay, so one is that, uh, so you know that in the site, you can evaluate this course. In pika.tamu.edu, you can evaluate this course. So I promise that if 70% of you or students, I cannot see your evaluation at this point, but I can see how much of you actually evaluate the class. So if 70% of students evaluate this class, then I will drop the lowest quiz from your quiz counting, right? So as you know, I already said this condition for the in the start of the semester when I using about the video quiz, but so it means that I will drop 2 lowest quiz in total in your count if 70% of students evaluate this class, and so drop the lowest score keys on your score. So it means that your score will be up. Okay, question? Oh, really? Oh, oh, okay. So, okay, let's check it briefly, but thank you for letting me know. Yeah, okay. So, oh, so it is not Pika, right? Oh, it's some different site. Okay, so, okay, got it. So, okay, so then, yeah, I report it and by finding some other emails. So, yeah, some evaluation site. So maybe it is from Howdy. I report the email, right?
Wait, Professor, are you talking about the course evaluation for this class? Oh, you can't hear.
So yeah, please evaluate this course so that the future AGs will be benefit from your evaluation, right? And assessment at tamu.edu. Okay, thank you. Yeah, thank you very much. So Karen says that, do you know how many students have already evaluated the class? I didn't know because I also got email in the 1 hour ago, but I will check it and let you know in the email. And Paula says that all students should have received an email from the evaluation site. Yes, I think that's true. So please evaluate the course so that your future AGs will be benefit from your evaluation. Uh, do you have any question on evaluation? Good. And the last one is about quiz 9. So yeah, I will just show how to solve the first problem of the quiz 9 in this briefly. Oh, give me a second. Because a lot of students had difficulty on solving some, especially solving the winning adjustment process. So that's why I just do it here. And also I'll give some just notice about the evaluation of quiz 8, because you can see that actually, yeah, quiz 8 is not evaluated in the campus. So I will show why. So, okay. So, okay, so that's the quiz 1. So Beth and Herbie are co-captains in some software team, and it really doesn't matter who does which task, but they disagree on how unpleasant particular tasks are. So Beth and Herbie decided to use this procedure by praising items as the other coach will handle this, right? So instead of they handle this job, they say that if they chosen some jobs, then it will be handled by other coaches, right? So it is kind of, reversing the thinking. Yeah, instead of preference, it is kind of the unpreference, right? So in that case, what you need to do is just do the same usual procedure on using the winning adjustment process, but with different, choice, right? So, okay, so let's just do it the same procedure as we did. So give me a second. I will share it in page 9. So here, that's his choice. And okay. And Harvey's point. Okay, I will just put it in here so that I can see what it is. Yeah, first job is selection of player position, and basis point is 9, Harvey's point 40, and coordination of game schedule, basis point is 9, Harvey's point is 10, and reserving the field. Oh, and is 9 and 11, and scheduling practice is 9, 12, and checking equipment 9, 13, and the last one is planning the end of season party, right? And that is 55, 14, right? So here, if you just use your winning adjustment process, then Harvey wins on selection, coordination, reserving, scheduling, and checking, but best wins on 55, right? Okay, so in that case, bestest point is 55, but Harvey's point is, if you add all the things, then what you can get is 86, right? So again, here Harvey is winner. So we need to bring some items from Harvey to Beth, right? To adjust it. So to do this, you need to calculate the profit ratio. Here, profit ratio is 40/9, 10/9, 11/9, 12/9, 13/9. But instead of just calculating actual, decimal points of those numbers, you can see that their denominators are all the same, right? So the the numerator with the smallest one gives you the propy ratio with the smallest one, right? And here, that is the first one is coordination of the game schedule, right? So, okay, so first just checking that if we just add 9 points in best and just take the 10 points from Harvey, because when we just drop this item of coordination of game schedule from Harvey to best, then best will get 9 points again, but Harvey's points drop to 76, right? So then their points should be 76 and 64, but still in this case, Harvey win, right? So in that case, you can just let this coordination of game schedule belongs to Bass and not Harvey. Then you can move on to next preparation one. So that is the reserving the field, because 11 is the most smallest numerator among all others. Then again, if you just add 9 points for Bass, but now taking 11 points from the Harvey, then what you can get is 73 for Bass, but 65 for Harvey. But in that case, winner and losers are changes, right? But that's what we want. So instead of giving whole jobs from Harvey to Bass, we will make them to share these items, right? So in that case, what we know is that Bass's item should be planning the party and the coordination of game schedule and part of, no, not full, but part of reserving the field, right? And Harvey's item is the remaining ones, so selection of player position and scheduling practice and checking equipment and part of reserving the field, right? Okay, does it make sense, or do you have any question on this process? Then the remaining one is to calculate their points and make their points equal by adjusting their portion of getting the reserve field, right? So in case of Bass, playing of this party is 55 points, and coordination of the uh, game schedule was 9 points, and part of the reserving period was 9 times x if we think x is the Bass's portion about the portion of reserving period belongs to Bass. belonging to Bass, right? So if you add all those points, then what Bass will have is 55 plus 9 plus 9x, right? And in case of Harvey, he has the selection of player position, which versus 40 points for Harvey, and scheduling practice, which versus 12 points for Harvey, and tracking equipment, which versus 13 points for Harvey, and part of the reserving the field. But in reserving the field itself is worth 11 points for Harvey, but he only gets parts, which is 1 minus x, because x is portion for Bass. So 1 minus x is portion for Harvey, right? So if you add all the numbers, then what you can get is 40 plus 12 plus 13 plus 11 times 1 minus x. And we need to make them equal, right? Because we don't want to have a loser or a winner. Okay. Okay. Do you have any question on this point? Good. Great. Then what you can see is 64 plus 9x is the basis point. And if you add all the number, then what you can get is 65 plus 11, so 76 minus 11x is Harvey's point. So if you read just 64 plus 9x is equal to 76 minus 11x, then by adding 11x, what you can get is 20x. Sorry. 64 plus 20x is equal to 76. And by taking negative 64 for each side, then you can get 20x is equal to 12. So x should be 12 over 20, which is 6 over 10. So in percent, it is 60%, right? So the reserving period is actually 60% is belongs to Bass, and this 40% is belongs to Harvey, right? Okay, does it make sense? Or do you have any question here? So that's the final answer if it is just, usual program. But here, again, if you just read the program statement, then the other co-chair will handle the item they choose, right? So in case of this passage item, actually here, that was actually Harvey will handle, right? This, and for here, this item, it is actually Bass will handle. So that's why in the exam, that's why in the actual the quiz, the answer of the number A, which says that which tasks will best do, is actually what Harvey chose, right? So that's selection of player positions and scheduling practices and checking equipment and part of the reserving the field. And for which of Harvey's will do is coordination of game schedule and playing the end of season party and they're part of the reserving the field. And so they share reserving the field. And here, who takes more burden for this task? So 60% is belong to Bass, but it means that Harvey will handle 60% of it, so Harvey will burden more burden on this task, right? So that's the answer of the first question. But I will give you some partial credit on the for those who just rightly chosen this, rightly apply this method, but the answers are different, then I will definitely give you some partial credit. So that's why I didn't put in number. Yeah, this is for Rust quiz. This is for Rust quiz 9. Yes. So, okay, so that's the solution of the quiz number 1. Okay. Do you have any question? Yes. Oh, in the exam. So yes. So in the exam 4, we cover 13, 14, and 9 only, and it is not comprehensive. So you don't need to study in the previous exam, just study on 13, 14, and 9, then you are fine. Good. Okay. No problem. Yeah, I understand. And also, it is not, oh, okay, there are some chatting questions. Oh no. And it is not fixed yet, but I will give you some kind of review session after Thanksgiving because I know that everybody do not hear anything on Thanksgiving. So yeah, and also including me, a lot of things are actually gone after the Thanksgiving. So I will give you some review session on that. So please stay tuned. Okay, okay, so that's the number 1 of quiz 9. And we will go back to the 14 if there is no question. So we explained about the paradox, and first paradox we dealt with is Alabama paradox. And Alabama paradox means that even if there has a house size increase, but some of the states lost its seat. That's the Alabama paradox, right? So in case of example 6.1, the size of computers increases from 46 to 47, but what actually each college will get as a computer is dropped from 2 to 1, right? Even if the house size itself goes up, right? So that's the Alabama paradox. And next paradox is population paradox. So here, population paradox means that actually, even if you have the, some largest relative difference, but you don't get any more seats because of that. So let's see this example first. So to deal with this, you need to calculate these numbers. So, okay, so use the Hamilton method. So we already calculated about the example 6.4 that compare the college population and make any cases for change of student worker. So absolute difference is L college has the maximal absolute difference, but M college has the maximal relative difference. So one of those two colleges will have some new student workers because their population will be increased, right? But if you actually use the Hamilton method to redistribute those positions, then in this case, the total number of population is 13,130. So it is 13,130 over 100 because there are number 100 student workers. So it should be 131.3. And your Q is just nothing but divide those population by S. So if you just calculate it, then what you can get is 42.4448. A Q is the quarter, right? So what I do is just divide the population by the standard deviation as what we calculated in here. Why do I need to divide it? So it is actually, that's a good question. It is actually came from the, on this example 5.4. So yeah, so it is actually continuation of the example 5.4. So we just assume that 100 students work a position here. Then we want to just distribute using Hamilton method when populations are changing. Okay, that's good question of it. So yeah, this is actually related to example 5.2, I think. Yeah, 5.2. This 100 came from this example 5.2. So here, if you just divide those numbers, then first one is 42.4448, and second one is 26.5118, and 29.5354, and 1.50080 divided by S. Yes, this 131.3. Yes. So always quarter Q is always the population divided by S in any method. Then in Hamilton method, rounded quarter is just the plural of the Q, which means that just round down your Q. So here it should be 42, 26, 29, and 1, right? So if you add all those numbers, then what you can get is 98. But we have 100 positions. Yeah. So there are 2 remaining positions here. And in case of Hamilton apportionment, those positions will be distributed for some states or carriages whose the fractional part is the greatest, right? So first of all, the greatest fractional part have is here R, and next greatest fractional part is given to K. So those will have the additional 1/6. So in Hamilton apportionment, there you have one more student worker position. So you can just distribute this 100% into each carriages, right? So that's the using Hamiltonian apportionment. Right. Okay, do you have any question? Mm-hmm. So I just add 1 for K and L, not the J or M, because K and L has the biggest fractional part, right? So biggest fractional part, the decimal part of the Q. Yes. Not the whole number, yes. Highest decimal number, yes. If you have the highest decimal number, then just give them 1. If you have the highest decimal number next, then give them 1, and so on. So that's the Hamilton method. Okay, then let's compare this proportion. So this Hamilton apportionment from 2014 came from the first example in the Hamilton apportionment. And this number, what we just calculated, is Hamilton apportionment for 2050. So it is 42, 27, 31, and the total is 100. So this apportionment changes. In case of J carriage, it is not changed. But in case of K carriage, the one position increased. But in case of L carriage, it is not changed. But in case of M carriage, one position was dropped, right? So, but we know that from the previous calculation, L has the largest absolute difference and M has the largest relative difference. So that's here. So we know that, yeah, even if M has the largest relative difference, but it loses one seat, right? One student worker, right? And K is actually has the some K gains some worker without any largest largest relative difference or largest absolute difference, right? So that's the called population paradox. So here, although M hat has the largest relative difference of population, it loses a student worker. And also K gained a student worker without largest absolute or relative difference. So the population paradox means that even if some states have the largest difference from the last year, or largest relative difference from largest year, largest relative difference from the or largest absolute difference from the last year, but they didn't get a new seat because of that in some times, right? So that's the called population paradox. Okay. Do you have any question? So again, this population paradox already happens. Yeah. This definition 6.5 is just population paradox. So it said it occurs when there is a fixed number of seats and reapportionment causes a seat to lose a seat to another seat, even though the percentage increase in the population is larger than the percentage increase of the state which wins the seat. So here, percentage of increasing the seats, which is just relative population difference of M is larger than relative population difference of K, but M loses the seat and K will get that seat, right? So that's called population paradox. So it is possible with Hamiltonian method, but it is not possible with the division method. So you can tell from the example that M lost a seat even though its relative difference is was higher than that of K, right? Gain the seat. Okay, is it good? Any question? Okay, so let's go to the new state paradox. So new state paradox, as name suggested, it occurs when a reapportionment when there are states is added. So United States is started with 13 states, right? But after time going on, the states increases from 13 to 50s, right? But this paradox will happen when in 1907, when Oklahoma joined the Union, and then there are some states who loses their seats without anything else, right? So it is possible for this paradox occur in Hamilton method, but not with the division methods. So that's why the current Congress adopts the Hill-Huntington method to avoid this kind of problem. So maybe, yeah, I'm not kind of political, but a lot of medias actually expected that Puerto Rico or Washington D.C. will be next, states if United States has a new state. So this kind of paradox will not occur in current Congress system, but in case of Hamilton method, it maybe happens. So we can see some example uh, what this paradox means in the actual case. So the preschool received 20 picnic tables to distribute to two age level groups, the 3-year-olds and 4-year-olds. And we wanna just distribute it using Hamilton method. So to distribute this, first of all, you need to find the standard divisor. And if you add those population, then what you can get is 190. So standard divisor is population divided by the house size. So it is just 9.5. And Q is, again, it is population divided by a standard divisor. So first one is 71 over 9.5. It is almost 7474. Okay, write down. And next one is 119 over 9.5. So it is almost 12.5 to 6. So the rounded quarter in the Hamiltonian method is just rounding down. So first one should be 7. Second one should be 12. So if you add those seats, then you got 19 seats. But we have 20 picnic tables. So there are one remaining table here. And then if you just comparing the decimal parts of quarter, then 4-year old has the larger decimal part, which is 0.526, which is greater than 0.74 from the 3-year old. So we need to add those tables into the 4-year old. So finally, 4-year old has 13 tables, and 3-year-old group has 7 tables, right? So that's what Hamilton method distributes those tables, right? Good. Okay, then let's think about the case when 2-year-old's class was added and it has 51 more students, right? And also 5 additional picnic tables were purchased for additional students because we just think that if we just divide 51 divided by 9.5, then it is almost around 5.38 things. So maybe Congress people saying things that, well, so if we just add 5 more tables, then maybe it just it satisfies the demand of the 2 years old. So redistributing those tables, in this case, we have 25 tables using Hamilton method. And to do this, first of all, we need to calculate the standard divisor. So here, if you add all those numbers, then it should be 241. So it is 241 over 25. And if you use calculator, then it is just 9.64. So now you understand why this is 25 instead of 20, right? Because we have 5 additional picnic tables. So that's why we divide the whole population not by 20, but 25. Does it clear? Mm-hmm. No, in the previous case, I just divide the whole population by number of tables, right? That's why we got 9.5. Yeah. But here, again, I just want to divide the whole population by the number of tables. That's why how I got 9.64. Yeah, actually, yeah, in one question, it contains 5 more calculations regarded. Right. Okay, then your quarter Q is just your population of each state by divided by standard divisor S. So first one should be 51 divided by 9.64, which is almost the same as 5.29. And next one is 71 divided by 9.64, which is almost same as 7365. And the last one is 119 divided by 9.64, which is the same as 12.344. So here rounded quarter is just rounding down your quarters. So it is 5, 7, 12. And if you add all those numbers, then it is 24. So you have one remaining 6. So in this case, just pick the groups with the biggest decimal parts. And here, the biggest decimal parts came from the 3 years old. So we will add one table to 3 years old. So final division should be 5, 8, 12 for each group, right? So let's compare this with the previous case. So in the previous case, 3 years old has already 8 tables and 4 years old has 13 tables, right? But by adding 2 years old group with 5 more tables, Now serial source have 8 tables, which is increased by 1, but Fourier source has actually 12 tables, which is just decreased by the previous one, right? So if you are parents in Fourier source group, then it seems unreasonable, right? Because your population was not changed, but your table was lost without any change, right? So that's why we call it as a new state paradox, right? Does it make sense? So here, in this example, adding the new state, which is in this case, it is just 2 years old, with proportional number of tables causes another state, in this case, 4 years old, loses a table. Right? Okay, do you have any question on this example? Good. Okay, next example is about the quarter condition. So this quarter condition says that the number of assigned to each represent unit must be standard quarter Q, rounded up or rounded down. So that's the quarter condition. Which means that, yeah, if you have Q, which is just calculated by your population over the standard divisor, then your final apportionment should be the round up of your quarter or round down of your quarter, right? But actually, that quarter condition can be satisfied by the Hamilton method, but all divisor methods cannot satisfy this quarter condition. So let's see some example in the above. So a company will hire 200 new workers to one of the poor facilities. And these new workers will be apportioned using Jefferson method according to current production levels at each facility, right? So we want to just distribute these 200 workers for each facility uh, for their production levels. And to do this, if you just add all the number, so here production level is our new population. Okay. Oh, sorry. So if you add all the number, it should be 18,834. So it is 18,834 over 200, which is 94.17. So if you just divide each population by this standard divisor, then first one is 12,520 over 94.17, which is almost same as 132.95. And the next one is 45 55 over 94.17 is almost same as 48.37. And again, 820 divided by 94.17 is 8.60, and 947 over 94.117 is almost 10.056. Okay. So here, in case of Jefferson's method, so rounded quarter is again round down, right? So here it is 132, 48, 8, 10, but not the same as the Hamilton method. In case of Jefferson method, you need to calculate this DI, the new divisor, right? So in case of Jefferson method, it should be your population. In this case of Q, it is 12,520 over your rounded quarter plus 1, right? So first one is 94.135. And the second one is 45.55 over 48 plus 1, which is almost same as 92.959. And the third one, 820 over 8 plus 1, which is almost same as 90.22. And the last one is 947 over 10 plus 1, which is 86.0 something. So here, the greatest DI divisor should be from partially to Q. So we need to add plus 1 in here to get 133, 48, 8, 10. So what I need to say is that if you're just using rounded quarter, then there will be 2 remaining seats. So we will just distribute per seat to the per seat to Q to get 100, and also we need to calculate this divisor for Q again, because our Q has the different apportionment level. So it should be the population divided by 133 plus 1, which is almost same as 93.4. But all other numbers are the same because their apportionment is not changed. And then again, this per seat Q has the largest divisors. So Jefferson apportionment should be 134, 48, 8, 10 by adding plus 1 again, right? Okay, question? Yeah, I just add plus 1 to the biggest DI, biggest divisor. Overall, yeah, overall, yes. So in the first round, biggest divisor was from Q, which is 94 point something. So that's why I add first one. And again, I calculate divisor again because apportionment of the Q is changed. So I need to calculate the divisor of Q again. Then I will get 93.4. But still, this 93.4 is greatest among all other divisors, right? So that's why I add one workers again to the per seat Q. Does it make sense? Okay. Okay, any question in the line? Okay, then you can see that actually this example it violate the quarter condition, right? Because if we follow the quarter condition, then pulsatility Q has only approximate with 132 or 133, right? That's what round up or round down of the original quarter, right? However, in the Jefferson apportionment, they've got 134, which is greater than their roundups, right? So that's why this example shows the violation of the quarter condition. So violates quarter condition because 134 is the same as 132.95, which is 3, or the round down of this number, which is 132, right? So quarter condition says that when you just distribute those, seeds to the states, then the number of seeds each state will get should be the same as round up of the quarter or round down of the quarter. That's the quarter condition. But in case of Jefferson apportionment or some other, apportionment using divisors, then it may be violated, like this example, right? So that's called the quarter condition, and we says that all divisor methods will violate this quarter condition except the Hamilton method. Okay. Do you have any question? Yes, I use the pulsatility Q, and it's quarter. So small q is quarter. Yeah, 130. Yeah, that's what I use. Actually, that number is a quarter of Q, quarter of pulsatility Q. Yeah. And quarter condition says that this round up of the quarter of pulsatility Q or round down of the quarter of pulsatility Q, which is 133 or 132, should be the apportionment number. But in the Jefferson method, the number should the apportionment number of pulsatility Q is 134, which is greater than 133 or 32, right? So that's why we say that Jefferson method sometimes violate this quarter condition. Does it make sense? Okay, so, and some researchers, Belinsky and Young, found that no apportionment method that satisfies quarter condition is free of paradoxes, which means that the divisor method, like Hill-Huntington method, Jefferson method, or Webster's method, are free of the paradoxes, what we see in those examples, but they can violate the quarter condition, like in the previous example. But Hamilton's method may have paradoxes, as you see in the previous example, but does not violate the quarter condition. So they proved it in mathematically. So there one thing we can learn is that there are no one pair method about this apportionment. So if we just want to avoid such a paradoxes, then we need to violate the quarter condition. But if we just keep the quarter conditions, then we need to allow some paradoxes, right? So there are no preferences in the apportionment, right? So that's what we want to learn for business, right? Do you have any question? So let's deal with some examples. Then, oh, here Rainy has question. What happens if it violates the quarter condition? So do they have to choose another method? So actually that is, so there is no one answer for that question. So in case of, think about the Oklahoma case. So in case of Oklahoma, yeah, this new state was when Oklahoma joined to the United States, then definitely, so if you are state with like 4 years old in the previous example, with whose seats will be decreased because of Oklahoma, then definitely you don't like this Hamiltonian rule, right? However, if you are state like 3 years old, then who gains the seats because of Oklahoma, then you like the Hamiltonian rules, right? So it means that there are no one pair apportionment method in the world, right? So, so maybe it can be chosen by politically. So Hill-Huntington method is definitely chosen by politically because there are lots of states who has the, got the disadvantage from the Hamilton methods. So that's why Congress actually adopt the Hill-Huntington method to avoid such a paradoxes. But in some other words, like, you don't have such a many states, then maybe Hamiltonian method will still works, especially in the when United States has the 13 states, then Hamiltonian method was adopted even if they know the Jefferson method. So it depends on the kind of political situation and about kind of participation of the states. So that's not there is no good way to decide it. Okay, thank you, Rainy. Okay, do you have any other question? Okay, so then let's deal with some examples and compare it. So in the next one, so these are actually what we dealt in previous examples. So first table is for the distributing computers for each high school. So to high schools. And this HAM app means Hamiltonian method, Hamiltonian apportionment, and JAP app means Jefferson apportionment. Web app means Webster apportionment. Then this HH app means Hill-Huntington apportionment. And next one is just distributing the council seats to each town. And the last one is distributing the student workers, right? For each method. And you can see that in case of these distributing computers, actually north and south has the same number for each method, but for east and west, their number of computer will be changed if they use Hamiltonian method or if they use Jefferson method, right? So for west side, Jefferson or Webster's method is much more advantage for them. But for east side, Hamiltonian method or Hill-Huntington method will be advantage for them, right? And in case of the town, if you just compare those numbers, then for town A, Jefferson method is the most, profitable method for them, right? But however, for town B, Hamilton method and Webster's methods are definitely much more preferable for them. And for town C, they definitely hate the Hill-Huntington method because Hill-Huntington method gives them only one seat. But the town D and E, they definitely want a Hill-Huntington method instead of the Hamilton or Jefferson method, right? And again, also this table also shows that why the small state with smaller population definitely prefer the Hill-Huntington method. So in case of Hill-Huntington method, any small state can get their seats at least one. However, in other methods, they do not get any seats, right? So that's the example. And in the last table, it is about the distributing student workers to each colleges. It is not class, sorry. It should be colleges. Then you can see that college J prefer Jefferson apportionment, but college K prefer Hill-Huntington apportionment, but college L definitely hate the Hill-Huntington apportionment, and college M hates the Jefferson apportionment, right? So you can see that usually Jefferson apportionment is much more preferable for large states because, in the second example, the largest state is town A, but town A gets the most seats when they use Jefferson apportionment. And in case of student worker, again, College J has the largest population, but they've got the most seats from the Jefferson apportionment. So you can also watch, kind of, it is not always, low, but it is kind of the intention, tendency that large states prefer Jefferson apportionment, but small states prefer the Hill-Huntington apportionment or others, right? But if you're a middle state, then sometimes you don't like the Hill-Huntington method. So when you need to decide on what kind of apportionment method will be applied for your situation, then think about your population, then choose one of the apportionment which is most preferable for you, right? Okay. Do you have any other question on this example? Okay, then let's deal with one more example. Then we just end this chapter. So a town has 3 districts, and North District has population of 98,000, East has 26,000, South has 6,000. So total population is 130,000. Then apportion 10 representatives using Hamilton, Jefferson, Webster, and Hill-Huntington methods. So here we already know what the quarter is. So I use just quarter. And then in case of the Hamilton method, you need to use the rounded quarter as rounding down, right? So here, if you just rounding this, then 7 to 0 is the rounding quarter. So all you need to distribute is 9 seats. Okay, question? Anyone? The 13,000 came from the, yeah, that's good question. That's from standard divisor. I need to calculate standard divisor first, definitely. Thank you, Emma. So this standard divisor is just number of population over the number of seats, right? So here it is 130,000 over 10 representative. So that's why we have this 13,000. Good. Okay. Thank you for pointing out. Yeah. So here, one remaining seat here. And if you see the fractional part of the quarter, then north has the greatest fractional part. So it should be added to north. So final apportionment by Hamiltonian apportionment is 8 to 0, right? Greatest fractional part. And in Jefferson method, again, we use rounded quarter as the rounding down. So again, this is 7 to 0. But in this case, we need to calculate the divisor, di, and where di is calculated as it is just population over apportionment plus 1. So here, first one is population 98,000 over apportionment 7 plus 1, which is 90,000 over 8. And if you calculate it, then it is 12,250. And next one is 26,000 over 2 plus 1. So it is 26,000 over 3. It is 8,066.666 something. And the last one is 6,000 over 0 plus 1, but which is just 6,000, right? And here the Rogers divisor is cutting from north. So we need to add plus 1 to north to get Jefferson apportionment, which is 8 to 0, which is the same as the Hamiltonian method. And in Webster's method, here rounded quarter is not the rounding down, but it is just rounding the nearest integer, right? Which is just rounding the nearest integer. So here 7.538 goes to 8 because it is greater than 7.5, but 2 is just 2, and 0.461 goes to 0. So it is just 8 to 0. So that is just done. So that's Webster's apportionment. It's just 8 to 0. And lastly, for Hill-Huntington method, you need to calculate Q star first, which is just the rounding down times rounding up and just taking square root. So first one is 7 times 8 with square root, which is 7.4833 something. And second one is 2 times 2. It is 2 because, rounding up of 2 is just 2, but rounding down of 2 is just 2. So it is just square root of 2 squares. So that's why we have 2. And in case of south, it is rounding up and down of 0 and 1. So it is just 0. So if you just think about the number, then this 7.538 is greater than 7.4833. So the rounded quarter should be 8 because we just decide based on the Q star, right? Okay, question? Yeah. 2 times 2, because in here, quarter is just integer, right? In case of in the East, quarter is integer. It has, yeah, the whole number. Yes, not decimal. So that's why we have just 2 times 2 instead of 2 times 3. So, okay, I know the class is over, so you can go it, but if I just write down result, then it's 5 to 1. And using your Hill-Huntington method, you can just divide d minus, then what you can get is 7 to 1. So again, you can see that Hill-Huntington method is favored to smaller states. So, okay, I'm so sorry for extending the time. And if you have any question, I'm around here, so let me know. Bye. Oh, we have quizzes in this Thursday. That's the last one. Okay. Thank you. Mm-hmm. D is equal to population over the square root of n, where n is just the rounded quarter, times n minus 1, which is rounded quarter minus 1. Mm-hmm. Yes, 7, yes. So yeah, I'm a little bit skewed over in the last time, so I just want to make clear. So yes. And here we choose the smallest number because it is d minus. So we need to decrease our seeds instead of increasing our seeds. And when we decrease our seeds, we need to choose the smallest divisor instead of the largest divisor. And in this case, if you calculate this, then this should be 13,000 something. And this should be 18,000 something. And this is infinite. So the north should those should forgive one six, give up one six, right? Okay. Mm-hmm. 1 times 0, because it is 1 minus 1. So the number 1 came from the previous one, right? And it is in the divisor, it is infinity, right? Yeah, positive infinity, because if we just divide some number by 0, then it goes to infinity, right? But in the Hill-Huntington procedure, if we need to decrease our seeds, because here the number of seeds are 11, but we only have 10 seeds, so we need to decrease our seeds, right? Then what we need to choose is just, pardon? Yes. Yes, and if you just count infinite, that's okay, because infinite is greater than, greater than any number, right? So just picking the lowest number, then you're fine. I understand. Yeah, I understand. Yeah, and that's my objective, to record all the methods in one example. Okay. Mm. In the just ask me question if you need to cover the step, then I will definitely cover the step. But yeah, but what I originally intended is just give you some, possible questions like exam 3, then go over it. Yeah, go over. Yes, that's what I actually intended. But if you need, then please let me know that I can definitely go step by step. Okay, do you have any other question? Okay, do you have any other question in the Zoom, people? Oh, here's some questions. Will our final exam in December be over all the semester's material? No, it will be only for chapter 13, 14, and 9. And Destiny actually answers, great. It's not cumulative. And Karen says that at what time are we meeting for office hours? Oh, that's a good question. So, okay, so this is 53. So, but I need to go back to my house. So can you meet in 3:10, Karen? It will take only 10 minutes. Okay, sorry for wait, and I will see you in 10 minutes. Okay, so I'll stop the live, and if you have any other question, then please visit my office hour in 3:10 and see you in soon.